guys. No banjo today. I went back to the guitar. So that's how we're going to start this one. Well, good morning, good afternoon, good evening, wherever you're taking this today. Welcome back to Physics of the Universe. Love you guys all, and continue to keep your cell phones out while I teach. You can go back and rewind and get what you missed last time. Today we're going to be talking about something. We're still talking about the weather. So this is part 3 of our weather unit. And we're going to be talking about what's called the Earth-Sun relationship. Without the sun's super important. Without the sun, there is really no weather. All the Earth would kind of like settle out. The most dense air would go on the bottom. The lightest air would go on the top. But what the sun does is it just kind of stirs everything around. And how do we do that? Well, that's what we're going to talk about today. In this chapter, what would you expect? We can start off by talking about what's called the electromagnetic spectrum. Something that I wanted to get into a lot more in the class, but as every day goes with this, I'm not sure when we are going to continue on with the class. So we're going to review over what I wanted to cover about the electromagnetic spectrum and how it relates to the weather. We're going to be talking about how radiation, I just noticed I have a typo in here. It says radiation from the sun. It should say electromagnetic radiation from the sun is converted into thermal energy on the Earth's atmosphere and on the Earth. We're going to talk about why it's hotter in some places on the Earth and colder on others. It's a really important concept to understand when we understand global weather and global weather patterns. We'll also see how the seasons are caused by really 3 different things: the tilt of the Earth, the angle of the radiation of the sun, and the length of daylight. So let's get this going. When we're talking about electromagnetic radiation, we're talking about the sun emits a whole bunch of different types of energy. This types of energy is typically called radiation, and it's the way that energy moves. And you think about energy in different ways. You have electrical energy. That's where you have to actually touch a wire or something like that, in which there's electrical current going through it. When I say electrical current, really electrical current is saying electrons are moving through it. You can talk about thermal energy, where if you touch something and it burns your finger, well then it's hot, and that's thermal energy. Another type of energy we'll be talking about is what's called radiation. Radiation is a type of energy that can travel from one place to the next. You don't have to actually touch it. You don't have to be nearby to feel it. And it can travel through space. It's the only way energy can actually travel through space without touching or being kind of convecting through the movement of a liquid or a fluid. To understand this, I actually have a video here I want to show you guys that goes through and explains how electromagnetic radiation works. So I am going to kind of bugger out here and let you guys watch this.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves, which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
Okay, so what that did was go through and talk about what's called the electromagnetic spectrum, which is a way of talking about how radiation is moved through space from one place to another. And we're going to focus on how the sun gives off radiation and how it hits the Earth. Now, radiation is one of those things that people are, the word itself, radiation, makes you think of things like movies like The Hulk, where he gets hit with radiation and it changes his DNA in his body, and he turns into this marvelous green beast. Or I think Spider-Man had a radioactive spider. There's also kind of the bad things where a nuclear bomb goes off, it gives off radiation, and people die from radiation sickness. So we have a lot of these things where we think of radiation as being a bad thing. It's not really. Some of it, yes, some of that radiation can be harmful to humans. Some of it can be very useful. So let's take a look at this. Whoops, no, we don't want to watch this again. Let's take a look at this. This is a great picture I found online of showing all the different wavelengths of radiation. And that's really how radiation is defined, is the size of the wavelength, how big it is from one place to the next. And when you're looking at that radiation, what you're looking at is how far it is from this point right here, the crest of the wave, to the crest of another wave. Now, we do have some situations where the wavelengths are very, very tiny. We're talking microscopic. And we have some cases where the wavelengths are very large, like that of radio signals and TV signals. So what's dangerous? What's not dangerous? Well, what's not dangerous, I hope it's not dangerous, because we live in this world right here where we get radio waves, the information that is sent out from AM radio stations or FM radio stations or television stations, your cell phone, microwave ovens. That's all energy that's large wavelengths. And those large wavelengths, I know you've probably heard before, don't stand next to the microwave, you'll get radiation poisoning. No, that's not how microwaves work at all. What they do is they take safe radiation and they focus it into one area. And that causes the heat to go up inside of the object of the microwave. So these large wavelengths of radiation don't affect us at all. And notice, I hear this all the time. You shouldn't like sleep with a cell phone underneath your head, or you shouldn't put your cell phone in your pocket because it's giving off radiation. True, your cell phone is giving off radiation, but it's not going to hurt you because the wavelengths are so big. So why does radiation hurt you? When we start getting into these smaller and smaller things of radiation, first of all, let's talk about the important, before I get to this, the important part of this electromagnetic spectrum is what we actually see. This little small slither right here, this little small area of wavelengths of electromagnetic radiation is the only radiation that our eyes can pick up. Now, our eyes are sensitive to those colors: red, orange, yellow, blue, green, indigo, and violet. You take all those colors and you mix them together, you get white, and that's where we see white light from. So when you're looking at the sun, you're seeing sunlight that's being given off by the sun. You see it as being white light. But in reality, if you could take that white light and split it up, it's going to be broken up into red, orange, yellow, blue, green, indigo, and violet. In fact, that's what raindrops are doing when they make a rainbow. Basically, they're acting like little bitty prisms, and it breaks up that light into different colors. And each one of those colors is defined by the size of the wavelength. If you look over here on this side of the visible light spectrum, you can see that that would be the larger of the wavelengths. And this is really important, so make sure you pay attention to what I say right now. If red represents the largest of wavelengths, then what happens as we move across the spectrum, the size of those wavelengths gets smaller and smaller and smaller and smaller until we get to purple or violet. Before we get to red, we have what's called infrared. Now, infrared is a form of wavelength that's slightly larger than red, and our eyes can't see it. But we're not the only organism out there that has eyes. In fact, something like, say, a snake has eyes. A snake actually has eyes that is developed to be able to see in the infrared. So we can't see the infrared, a snake can. Why is that important for a snake? Well, a lot of snakes hunt at night. Well, when they hunt at night, they're looking for things that are giving off a warmth signature. And if I turned off the light right now, what you would see, in fact, I've got a little device right here. I don't know if you'll be able to see this tonight. What you'll be able to see is if you turned off the light, you would see something that was in the infrared spectrum. So this is called a thermal imager. And I'm going to make this a little bit larger real quick so that maybe you can see what I'm talking about. So this is called a thermal imager, which you're seeing right there in that image right there. You can see kind of my face. What you're seeing with my face there, something just came up, I want to get rid of that. No. Alright, so let's see. Hold a little bit closer there. What you're seeing is what your eyes can't see. I could turn off all the lights in the room, and this thermal imager would be able to see my face and the heat that's being given off. The heat that's being given off from my face is a form of infrared radiation, are larger wavelengths than what my eyes can actually see. Now, the thing about infrared radiation is snakes, like I said, have eyes that are adapted to see it. That way they can hunt at night. So they hunt something like mice. Mice give off heat. So they are able to go through and look and see where these little mice are by looking at their heat signatures. But they're not so much good in bright light. They're kind of overwhelmed by the other wavelengths of light that we typically take advantage of. As we go from infrared And I need to minimize this picture again. There we go. Put me small because I'm not important here. As we go from infrared, we go to red, which is the largest of the visible light wavelengths. We get smaller, smaller, and smaller until I get over here to purple. Purple, another word for purple, is violet. Then what happens is that's the last color that our eyes can see. As we move beyond purple, we start going into what's called ultraviolet light. Now, most of the light will reflect off of our skin, but now we're getting with ultraviolet light a wavelength of radiation that is so small that it possibly can penetrate some of the surface cells of your skin. Within the surface cells of your skin, there's DNA that knows, like if you get a cut, the DNA knows how to reproduce, get more skin cells to go through and make more skin cells, and then you heal, right? Well, in the case of ultraviolet light, if there's too much ultraviolet light, that might be able to penetrate some of those upper skin cells, and you might get a burn from too much radiation hitting your hand, or it might go through and mess up the DNA code that's inside the skin. And when it messes up the DNA code, then the code says, I don't know what I'm making, I don't know where it's supposed to go, and it sends it to somewhere else in your body. And that could be something that would be considered skin cancer. So skin cancer essentially is the possibility of something like ultraviolet radiation affecting your skin DNA, confusing the skin's DNA and making it do what it's not supposed to do. And it's something that the sun does give off ultraviolet radiation. It gives off infrared, it gives off visible light, it gives off ultraviolet. It even gives off, to some degree, X-rays and gamma rays as well, and microwaves and radio waves. It gives off a full spectrum on the electromagnetic spectrum. But it becomes dangerous as we start getting into the ultraviolet. The good news is that in our atmosphere we have a lot of things that absorbs the ultraviolet for us. So things like, for example, ozone. Up in the upper layers of the atmosphere there's a lot of what's called ozone, which is 3 oxygens bound together. And that will take in ultraviolet light. It will absorb it and turn it into heat, and we don't need to worry about it. This might be where you've probably heard we got to protect the ozone layer. Well, the ozone layer is what's protecting us from ultraviolet radiation. And some of these things that even get smaller wavelengths. As we still get into smaller, you've heard of X-rays before. You've probably gone to the dentist before. They put like a little thing in your mouth. The thing that they're putting in your mouth is film. Just like the film that they put like in old school cameras. So they put this thing into your mouth that's film, and what they do is they have a camera that goes through and that shoots X-rays into your face. Now the thing about X-rays is the wavelengths are so small that the soft tissue in your face will just go right through. And what happens when it goes through, it just burns the film that's on the other side of your mouth. However, X-rays cannot penetrate bone, like for example teeth. So what happens is the X-rays are either absorbed or reflected off of your teeth. So whereas X-rays can be dangerous if you're exposed to them a lot, small doses of X-rays, well, we're kind of used to it anyhow. We get that from the sun, we get that, well, from the universe actually. So we can deal with small doses of X-rays. But if you've ever noticed when you go to the dentist, the person leaves the room, that's so they're not hit by X-rays constantly over and over and over again. But what it does is on that image, it burns, so the dark part is burnt, and it can't burn where your tooth is. So it's left the white part behind where the image, the film has not been burnt. And that's what you're looking at as an X-ray. So when you're looking at these things like X-rays, you're seeing bones. The dark stuff is where the X-ray has burnt the film. The white stuff is where the X-rays couldn't go through the bone to get to the other side. Then we start getting smaller and smaller and smaller in wavelengths to things that are definitely dangerous, that can penetrate the skin, that can penetrate your tissues, and even penetrate your bones. And once again, small amounts, it's okay. Whenever you walk across granite rock, granite has a small amount of radiation that comes out of it. Small amounts are okay. We can survive with it. However, when we start talking about being around nuclear power plants, they have large amounts of radiation coming out of it. Large outcroppings of granite rocks, people have radiation detectors in their houses to help them detect that radiation. That becomes more and more problematic. But what I really want to focus on for today is this part of the spectrum right here, the infrared, the visible light, and the ultraviolet light. This is where most of the energy is coming from with the sun. So, the sun gives off this radiation. It travels through space, and it travels forever through space. There's nothing ever that's going to stop that radiation from going through space unless it runs into something, for example, like the Earth. But the sun puts out a tremendous amount of, radiation. So, what does the Earth do with that radiation? Well, that radiation is really so important for us. Well, if we take a look at this chart right here, what you can see is that here is what's called the energy's budget. This is our income of radiation from the Earth, and the outgoing would be the outcome of where it's going. How much gets deposited, how much gets withdrawn. So think of it like a bank. And if we're putting in, say, 340 radians of energy, think of that as $340. So what happens to that amount of energy? Where does it all go? Well, 77 radians of that, that is absorbed by the atmosphere. I told you earlier that the sunlight, things like ultraviolet light, gets absorbed by things like ozone, carbon dioxide, methane, water vapor. All of these things are being absorbed by the atmosphere. And that's actually important, because if the atmosphere is absorbing that sunlight, it just doesn't it's not like the rays get stuck in the atmosphere. The rays get changed into something different. In other words, when I say they're changed into something different, their wavelength changes. So it comes in as visible light, and the atmosphere kind of sort of slows that wavelength down and changes it to a different form of radiation called thermal radiation, or as you would probably recognize it as heat. So the sun actually shoots light at the Earth. The Earth's atmosphere will take that light radiation and turn it into heat, and that's what keeps us warm. This is important. We don't want to overheat, but we also don't want to go cold. Remember, we talked about Mercury earlier in the year. Mercury has no atmosphere, so the side that's facing the sun is super hot, but the side that's facing away from the sun is the coldest point on any planet in the solar system, because the air is not there to hold the heat in. So our atmosphere absorbs about 77 of that 340. About 77 of that is reflected back into space. So if you go to the moon and you're looking at the Earth, you're seeing reflected light. Earth doesn't give off its own light. What you're looking at is light that's reflected off of the sun. That's really what you're kind of seeing, is that 77 is reflected by clouds and atmosphere. Another 22% of that, 22 parts of that 340 is reflected by the Earth's surface. So now if you add up 22 and 77 and 77, that doesn't come to 340. So where does that all go? Well, it's either absorbed into the atmosphere, or most of it's absorbed by the Earth's surface. And this is really important. The Earth's surface is taking in that radiation, and it's converting that wavelength into thermal radiation, in other words, heat. So it takes in sunlight and turns it into heat. And when it turns it into heat, in turn, it actually heats up the atmosphere, and it gets moved throughout the atmosphere. So not only does the atmosphere get heated up by the radiation, the atmosphere is also being heated up by the Earth, which is absorbing the sun's radiation as well. So what happens to that heat? Well, it turns into infrared radiation, heat, and the Earth gives off that heat. So if you could turn off the sun and look at the sun through my special little device, you would actually see the Earth is glowing. It's giving off heat. If you go to the moon and look at the Earth from the other side, you'll still see the heat. In fact, meteorologists, people who watch the weather, are really looking at where is the heat in the air, because that's going to be really, really important as determining what's the weather doing at any given time and what it's going to be doing in the near future, which is really what we're talking about. Some of that heat is just given back off into outer space as well. So we have light being reflected into space. We also have the Earth giving off heat, and that's going to go back off into space. But really, a lot of it gets either A, reflected back to the Earth by the clouds. So we're kind of trapping that thermal radiation, that infrared radiation, that heat. Or the greenhouse gases are also heating the Earth back up as well. And greenhouse gases, that's the things like ozone, water vapor, methane gas, SO4, what did I forget? CO2, that big obvious one. That's actually heating the Earth up as well. So we kind of get this feedback loop of sun heats up the Earth, a lot of it gets reflected back, a lot of it gets spent back into space, but we do trap a lot of it because of these greenhouse gases. Some of this other stuff we call latent heat, thermal conduction and convection, evapotranspiration. Evapotranspiration is where plants are actually taking water vapor and put it into the air. They have to give off heat to do that. But that's kind of an overview of how that energy is being used. The first thing that's kind of important to find out, how hot is it going to get? How do we determine how hot we're going to be? And here I've got a picture. This is a picture taken in the floor of my house because, well, you know, we're all trapped inside right now. We can't get out because of the the COVID-19 coronavirus. So it's not like I can go out and do too much right now, but I was able to go through and take this lamp, and what I did, you can see it right here. Here's a picture of the lamp. I took the lamp and I aimed it at the ground. You can see it's really bright on the ground. And I want you to notice that the lamp is hitting the ground at about a 90-degree angle. All right? And then I'm going to press play here, and you can see there's no talking or anything. I'm just going to reach down. I'm going to grab the lamp. And I'm going to just haven't changed the lamp at all, but you'll notice that now the lamp is at an angle, at a 45-degree angle. And that means that that light is not near as bright as it was before. The intensity of radiation coming from that lamp, because that lamp's giving off visible light radiation, when it was pointed straight down, it was shining on the ground and it was really bright. But now I'm having to take the same amount of radiation and cover a larger area because I turned it at an angle. And when I turned it at an angle, it wasn't as bright. Well, what does that mean to the ground? Well, if I shine it back onto the ground, if I go back to the beginning here, if I shine it onto the ground, and that's where we're getting the most intense radiation, what's going to happen is you're going to get something that looks like this. This was taken with my infrared camera on my iPhone, and you can see this is the temperature. This is how much heat is being given off. It's about 26 degrees Celsius. That's a little warmer than room temperature. I didn't actually have it sitting there for too long because I didn't want to overheat my floor and warp my floor. But with the infrared camera, I was actually able to go through and get a little video of me doing the same exact thing. So here I am. I'm about to take that infrared camera. This is the hottest point right here. And I'm going to reach down and grab the light, and I'm going to spread it out over a large area. And what you'll see, first of all, the ground stays hot after I turn the camera, after I turn the light. But now the floor over here is starting to heat up where I've aimed the light at it. But what you'll notice is that it's only getting to about 22 degrees. That's actually pretty close to the room temperature in the room. And the longer I leave it there, it's really not going to change that much. So because I've changed the angle of the camera, I've changed how much I'm actually heating up the surface of my floor. Well, this works with the Earth too. And, oops, next slide. This works with the surface of the Earth too. If you've ever wondered why is it so hot at the equator but not at the North Pole, okay, not a lot of people wonder that. That's just a fact that everybody knows. It's ice on the North Pole and it's hot at the equator. But why is that? A common misconception on this is that the reason why it's so hot at the equator is because it's closer to the sun. That's not true. I usually do this example in my classroom. I have a marble. I walk to the other side of my classroom and say, this marble represents the Earth. The wall on the opposite side of the classroom represents the sun. There's not that big of a difference between where the equator is versus the North Pole. So why is the equator, now that we know that, why is the equator so hot? Well, if we look at this time, now this is a generalized time on the Earth, you can see that this time, at this moment, the sun is hitting the equator at a 90-degree angle. That's the steepest angle that you can get. So the sun's shining directly on the equator. If we go up a little bit further north, right here, this is what's called the Tropic of Cancer. It's not hitting at 90 degrees. That light's being spread out over a larger area. And as we move north towards where we are, light becomes more spread out. Now here in the Pacific Northwest, we don't have as much, it's not as warm as it is at the equator. And then finally we get to the North Pole, light is going to be hitting it almost level to it. In fact, on this particular scenario that I've got drawn here, the North Pole, the sun would be at sunset all day. So it's all kind of like skipping across the surface, which means it's not heating the surface up very much. So the North Pole doesn't get that much solar radiation. It doesn't get, I want to say, not that much, that intense of solar radiation. The more intense solar radiation is right here. Now you guys notice I always wear a hat, right? One of the reasons I wear a hat is because when I go outside, I am susceptible to getting my head burned. When I go out and I mow the lawn, I live up here in Washington. When I go out and mow the lawn, the sun doesn't burn me right on top of my head because the sun's never directly overhead here. It always burns me at an angle in which it's hitting the most intense angle. So I'll get like a little halo when I'm out mowing the lawn at about 47 degrees, which happens to be, by coincidence, by no coincidence really, the latitude that we have here in the Pacific Northwest. If I were to go to the equator on this day that I've got drawn here, that is where I'm going to get sunburn on the top of my head. And that's the importance of wearing a hat. Okay, I didn't need to wear one today. It's weather, and so this is a vanity thing. So, I thought about that. I'm like, well, how can I show you guys? I can show you in school so much better, but how can I show you guys at home? Well, here I am. You can see I'm back with the lamp on the floor downstairs in my house. And this is just a picture, not a video, but you can see I'm shining. You can see it's really, really bright right here. That's because it's getting the highest angle of light. As we go further and further north, the brightness becomes less intense. So if we look at this in a thermal camera, you can see that there's the temperature right there. I'm shining it on the globe. It's at 29. It's actually pretty warm. I'm getting my globe pretty warm. But the further we get away from that direct sunlight, the cooler the globe is getting. And that's how it actually works on the Earth. The more direct sunlight that you get from the sun, the hotter it's going to be. So why do we have seasons? Why is it hot in the summer yet cold in the winter? And by the way, just exact opposite in the southern hemisphere. Their winter is our summer is their winter. Why does this happen? Well, the sun happens to only be, if I go back a couple slides here, this only happens 2 times out of the year. When the sun is directly, don't point at the screen, Mr. Lee, nobody can see that. The sun is directly above the equator only 2 times out of the year. So 2 times out of the year, can you go to the equator and have the sun directly on top of you? Those 2 days are called the vernal equinox, the first day of spring, and the autumnal equinox, the first day of fall. And that's the only day, if you're on the equator, that you could look straight up at 12 o'clock noon and see the sun. Every other day, you're either having to look to the north or to the south to see where the sun is at noon. Here in the Pacific Northwest, we always have to look south. We never have the sun directly above us. If we move to other points of the season, let's say, for example, winter. During winter, the Earth, I forgot to go back. I need to go back and mention this. The reason why it changes from summer to winter is because the Earth is tilted. The Earth is, if you've ever seen globes are never straight up and down. They're always tilted. And that tilt is about a 23.5 degree angle of tilt. And as the Earth goes around the sun, it always stays with that same tilt. So what happens is that here's the first day of spring, the first day of autumn, the sun is shining most directly on the equator. But as we move from spring into, I guess we're going this way. As we move from spring into summer, notice that the northern half of the globe is now pointing more towards the sun, which the sun is going to be shining directly on this line right here. That line is called the Tropic of Cancer. It's about 23.5 degrees north. Where did I say 23.5 before? Well, the Earth is tilted on an angle of 23.5 degrees. So why 23.5 degrees north? Well, latitude is kind of based on the circular curve of the Earth. If you tilt the Earth 23.5 degrees, then from the equator being 0, you would go up and it would be at 23.5 degrees. So on the first day of summer, what's called the summer solstice, that is where the sun, you would have to go to that latitude and look straight up, and that's where you would see the sun. Then every day it would be changing and be changing until we get to the autumnal equinox. Then it would be changing and changing until we get to the winter solstice, where the sun is going to be directly above this latitude right here, which is called the Tropic of Capricorn, which happens to be 23.5 degrees south. There's that number again, 23.5 degrees. It keeps coming back up because that's the tilt of the Earth. So depending on where we're at in the orbit, note that our summer, we're tilted more towards the sun. So here we are. Seattle would be located about right here. We look and see that, look at the angle that the sun's hitting the Earth here. So that's going to be our first day of summer. Also look over here. So Seattle at this point, this is our winter. Now Seattle's way up here. Look how low that angle. So the sun's going to be at a much lower angle here in the Pacific Northwest. In fact, the highest the sun ever gets, we always have to look south to see the sun. This picture was, oops, go back one. This picture was taken, this image was taken first, I think somewhere like Boston or something like that. So it's not quite Seattle, but we're pretty close. In Seattle, on the first day of summer, that's where the sun is going to be at its highest point. We only get to about 70.5 degrees above the equator. So we still have to look south, but it's actually pretty high in the south. But when we get to the winter, when we're in school, probably about the last time I saw you guys, you'll notice that the sun rises in the east and just kind of goes barely above the trees. It doesn't get very high at all. You go at 12 o'clock noon, you'll see the sun just barely above the trees, and then it sets in the west. The highest that it gets is about 23.5 degrees in itself. So we'll always have to look to see the south, and depending on the time of day, that is where the sun is going to be. So how do we know, how can we figure out when this happens? Well, if you've ever looked in the globe and seen something like this, this is pretty common. Most globes have something like this, and nobody really actually knows what it is. Well, I'm going to tell you what this is. This is called the anoloma. And what the anoloma is, you'll notice that it stretches from this dotted line right here, that's your Tropic of Cancer. This is your equator, and this dotted line is the Tropic of Capricorn. And this is something that humans have known for a long time. The anoloma, this figure right here, will tell you what day where would you have to go to see the noonday sun directly above you on a particular day. For example, my birthday is August 29th. You guys can feel free to give me presents, but usually before school starts. If we look at it right here, here's August right here. So on August 5th, it's going to be at that latitude. 10th, it's going to be about that latitude. And we're going to get to about August 29th. And you can see the sun on my birthday is going to be about right here, which is going to be somewhere between, there's 23.5 and the equator. So we can actually figure out when that's going to be. What's even more clever about this is that you don't have to be at the equator. By the way, if you went through and took a picture of the sun every day, that's what you would get. You would actually get something that looks like that. Sometimes in the summer, right here, you'll see that the sun is at its highest point. And in the winter, it's going to be at its lowest point. So if you actually marked at the same time, at the same place every day, this is what the sun would look like. This is called the anoloma. And if you've seen the movie with Tom Hanks, it's getting to be kind of an old movie now, so I'm not sure anybody's actually seen it anymore. But in the movie called Castaway, that's the one where Tom Hanks is trapped on an island. His best friend is Wilson, the volleyball. He goes into this cave, and the sun's shining through a little crack on the cave, and you'll notice that he's gone through it and he's marked every day where the sun's at, and you can see that's the anoloma. So he's using that to mark the time of year, because I think in the movie he was there like 3 or 4 years or something like that. I have to go watch the movie again. But that's how long he was trapped inside that cave. And this is what people used to do. They used to look at where's the angle of the sun to determine at 12 o'clock noon what day it is. So if you know what latitude it is, you know the angle of the sun, you can figure out what time of the day it is. You don't need a calendar, you don't need an iPhone, you don't need your watch. You can actually go through and figure that out. And we can actually go through and chart, whoops, go back. We can actually go through and chart where this is going on. So this is a chart, this is like, has all the latitudes on here. So like I said, my birthday was on August 29th, so August 29th would be about right here. So if I wanted to go where I was getting the most intense sunlight, I'm like, hey, I told my wife I want to get away, I want to go to where there's lots of sunlight. In fact, I want to go to where there's the most sunlight possible. Where I would want to go is about 10 degrees north latitude. So you can look on your birthday and figure out where you would have to go look at it. And I'm going to get people who ask me, why is it a figure 8 shape? Well, the reason why it's figure 8 shape, you can see this little GIF right here, this little animation. The Earth doesn't go around the sun in a perfect circle. Remember that the Earth's as it goes around the sun, is sometimes a little bit closer, sometimes it's a little bit further away from perfectly circular orbit. And because it's a little bit closer and a little further away, if you remember Kepler's laws, when we're closer, we're moving a little faster. When we're further away, we're moving a little slower. So that kind of gives us a reason why we have that classic figure 8 shape of the anomaly. So that helps us to determine where on the globe is getting the most intense sunlight. And where they're getting the most intense sunlight is why they're getting so much heat. But that's only part of the story. Another part of the story as to why the Earth gets heated like it gets heated is by looking at the length of daylight. How long is your day? Now, if we look at the scenario where the sun is directly above the equator, this is a day called the equinox. Equa means equal, Latin for equal. Nox is another word for night. In fact, Nox is the goddess of night. And on that one day, or 2 days out of the year, the vernal equinox, the autumnal equinox, that's where the sun's directly above the equator. But something else happens. We have what's called the circle of illumination. And that is the separation between day and night everywhere on the globe. So everything on this side facing the sun is in the day, and everything on this side is facing away from the sun is at nighttime. And if you look at it right here, all the way from the North Pole to the South Pole, everybody is has the same amount of facing away as they have facing towards it. However, if we go to our summer, you will see that here in the North Pole, if we take that globe and we spin that globe around, then what's going to happen is the North Pole is never going to have night. So if you live in the northern latitudes, if you live in any place above the Arctic Circle, you're going to get 24 hours of daylight. I've been there. I've been to Iceland during the summer, and it was really weird to be midnight and the sun was just on the horizon. But you also will notice that if you're at these latitudes, this is about the latitudes that Seattle's at right here, we have this much sunlight and about that much darkness. So we get a lot more sunlight than we do darkness. In the southern hemisphere, it's just the opposite. If you're at that same latitude, you're not getting very much sunlight and a lot of darkness, which means we're taking in more solar radiation during the day. We're getting a more intense sun angle, and we're taking in longer radiation. Those two things combined together will actually give us our summer seasons, why we're warmer in the summer. Now, as we get to the winter solstice and the Earth is tilted away, all this is opposite. Then, Antarctica, the South Pole, will be in 24 hours of daylight instead of 24 hours of night, and the North Pole will be in 24 hours of darkness. So, in fact, the North and South Pole, directly on the North and South Pole, they remain either in daylight or darkness until the equinox. The day of the equinox, they get a 24-hour sunset or sunrise, and then the sun goes down for the rest of the year, or the sun comes up for the rest of the year. Everybody else, it becomes uneven. The only day that it's even, the only 2 days are even, are on the equinoxes. So, in the summer, It's hotter not only because we have longer days, but also because the sun is much higher angle, thus more intense. And in the winter, the sun angle is low and the days are short, so that's why it's so cold. And that's kind of where I'm going to leave it off today. That doesn't explain everything, but it does help us to understand why we get the weather that we do. Next time I talk to you guys, you can see I've got two shirts. I've got a black shirt, I've got a white shirt kind of hanging off the awning of my house. And yeah, I know I need to do some cable management with those lights. What does this have to do with what we're going to talk next? Well, we'll see that in the next presentation. And that actually those two shirts become really important in helping us to understand why the weather is like it is. So that is going to be it for today's presentation. I want to thank you guys all for kind of hanging through this, and I found out today that I am going to be able to give credit to people who are watching these videos. There are going to be assignments associated with these videos eventually, and some quizzes associated with them. And what's going to happen is I'm going to be able to give you credit by doing the assignments and the quizzes associated with it that will only help your grade. So if you've got a grade that's not great right now, before the hiatus, this might be your opportunity to fix that. So with that said, I hope to see you guys soon. I really do. Love you guys, and we'll see you next time.